Trigonometry, Chapter 5, Trigonometric Identities, Section 3, Sum and Difference Identities, Video 5, Using Sum and Difference Formulas, Example 1. This series is based on content from Pearson's Trigonometry 12th edition by Lial, Hornsby, Schneider, and Daniels. In the previous video, we derived sum and difference formulas for sine, cosine, and tangent. Here's all 6 of them. Just remember, when you see a plus minus and a minus plus in a formula, that's condensing 2 formulas into one. To extract the 2 formulas, you either use the top sign on each pair, so plus and then minus, or the bottom sign on each pair, minus then plus. If they match, like in the sine formula, then it's either 2 pluses or 2 minuses. And when you have them all over the place, like in the tangent formula, it's either all top signs or all bottom signs. So it's either plus, plus, minus, or minus, minus, plus. In this video, we apply these formulas to evaluate trig functions at new angles. Before I jump into it, I want to remind you about something on the unit circle. When we did the unit circle before, we had 0 degrees, we had 90 degrees, and we had 45 degrees, not drawn to scale because I'm using a mouse. But we also had 30 degrees, and we had 60 degrees. This is drawn horribly. Now, if you notice, the difference between adjacent angles is not the same. From 0 to 30 is 30, but then up 15, and up 30. If we were to go up 15s, this would be 15 degrees, and then between 60 and 90 would be 75 degrees. So the unit circle seems to be a little bit deficient in the sense that the angles don't go up by the same amount each time. But if they went up by 15s, we would pick up 30, 45, and 60, but we would also pick up 15 and 75 degrees. We now have the ability to get trig functions for 15 and 75 degrees, amongst other angles. For example, we're going to find sine, cosine, and tangent to 75 degrees. Now, until now, we didn't have the means to determine trig functions of 75 degrees. However, since 75 degrees equals 30 degrees plus 45 degrees, we can use sum formulas. Since we'll be using both 30 degrees and 45 degrees, let's quickly recall both special triangles. In the 45 degree, 90 degree triangle, we label the 2 legs as 1s, and the Pythagorean theorem gives us a hypotenuse of the square root of 2. And in the 30, 60, 90 triangle, the side opposite the 30-degree angle is 1, the side opposite the 60-degree angle is square root of 3, and the hypotenuse is 2. So get ready to use these triangles if you don't have your trig function values memorized, which is okay, as long as you can derive them quickly. These, along with trig definitions, will give us any trig function of 30, 45, and 60. Yeah. Now let's find sine of 75 degrees. So the first thing we're going to do is rewrite 75 degrees as 30 degrees plus 45 degrees. That's pretty easy. But now we can apply the sine sum formula. Should have put the word sine here, not its abbreviation. But I digress. Sine of A plus B equals sine of A cosine B plus cosine A sine of B. Yes. Sine of A plus B equals sine of A cosine B plus cosine A sine of B. I have them memorized, but you might have noticed I looked up into the back of my head to make sure that I was saying it correctly. Now, I know all these functions' trig values thanks to these triangles or the unit circle, or however you get these trig function values. Some people sit down and try to memorize them all. That's great. I would rather understand than memorize. If I didn't, I could whip out these values so quickly you would think they were memorized. But sine of 30 degrees is 1/2. Cosine of 45 degrees squared to 2 over 2. Cosine of 30 degrees is squared to 3 over 2. Sine of 45 degrees is squared to 2 over 2. And if we were to multiply, we would get the square root of 2 over 4 plus square root of 6 over 4, and we can put that together into a single fraction. And that's it. Sine of 75 degrees is square root of 2 plus square root of 6 over 4. Weird, but correct. Using the same approach, we could evaluate cosine of 75 degrees. I'm not going to go through all the details. They are written here. There's the pen. But if we rewrite 75 degrees as 30 degrees plus 45 degrees, and then apply the cosine sum formula, which is the product of the cosines minus the product of the sines, and then evaluate all the trig functions, multiply and then add because we have a common denominator, we would get the square root of 6 minus the square root of 2 over 4. So we have the value of sine of 75 degrees, and the value of cosine of 75 degrees. What about tangent? Well, remember that the tangent formula uses values of tangent. We go back here, we can see that. The tangent sum or difference formula uses only tangents. So if we're going to do tangent of A plus B or A minus B, we need to know the tangent of A and the tangent of B. There we go. So tangent of 30 degrees is square root of 3 over 3, and tangent of 60 degrees is not what we needed there. This should say tangent of 45 degrees. I think this is fixed in a future slide. I remember correcting this earlier. Tangent of 45 degrees is 1. I just don't think I corrected it in all of the slides. Yep, there it is. So tangent of 75 degrees equals tangent of 30 degrees plus tangent of 45 degrees. But the tangent of a sum is the sum of the tangents over 1 minus the product of the tangents. So now I just have to substitute all my values. Tangent of 30 degrees is square root of 3 over 3, and tangent of 45 degrees is 1. Now you notice that when I went from here to here, I went ahead and did square root of 3 over 3 times 1 to just get square root of 3 over 3. And that is what we have for tangent of 75 degrees. Now, that is not a good final answer, not the least of which reasons is it's a fraction with fractions inside of it, so we need to fix that. To simplify this, we're going to multiply both sides of this fraction by 3. It's standard fraction clearing protocol in a complex fraction. Multiply both sides of the large fraction by common denominator of the smaller fractions, like that. And when you distribute it, what will happen is it will cancel the 3 in the denominator, but the 1s will become 3s. And we end up getting square root of 3 plus 3 over 3 minus the square root of 3. This is a better looking answer. Should we go further and try to rationalize the denominator? Yes, and it may not be obvious why, but watch this. If you want to rationalize the denominator that has a square root, but that square root is part of an addition or subtraction problem, then you multiply both sides of the fraction by the conjugate of the denominator. The conjugate is just the addition version of the subtraction problem, or if it were an addition problem, it would be the subtraction. In other words, you change the sign in the middle. So we're going to multiply both sides by the conjugate of the denominator, because that will create a difference of squares on the bottom and eliminate all the square roots. If you were to FOIL all this out, we'll just play it out real quick. This is 3 root 3. Root 3 times root 3 is root 9, which is 3. On the inside, 3 times 3 is 9. And the last is also 3 root 3. So we would get 12 plus 6 root 3. And in the denominator, we would get 3 squared is 9. The outside and inside products would cancel. And the last part would be minus the square root of 3 squared, which is 3. So we would get 12 plus 6 root 3 on top and 6 on bottom, which is what we have here. But then we can split this into 2 fractions and reduce it. We can reduce this fraction and this fraction. They both reduce to non-fractions, and we get 2 plus root 3. 12 divided by 6 is 2, and then the 6's cancel on the root 3. This is clearly a much better looking answer than that. Nobody's going to argue with that. That's not bad. I mean, that's better than this. That's better than that. But this is not as good as that. So rationalizing denominator is nice. And here's our values of sine of 75, cosine of 75, and tangent of 75. And now that we have these, if we went back to the unit circle, went to 75 degrees, because we now know the value of sine and cosine, if you absolutely wanted to, you could put the value of cosine as the x-coordinate. And for symmetry, I'm going to write the sine coordinate with the 6 first. And this technically could be a point on the unit. It is a point on the unit circle. It's just not a convenient point on the unit circle. Oh, by the way, we could have also evaluated tangent of 75 degrees as follows. We could have written a quotient identity of sine of 75 degrees over cosine of 75 degrees since we have those answers. Multiplied both sides of this by 4 to get this, but this would still require rationalizing the denominator. I challenge you to rationalize the denominator and show that we still get the same answer. Now you try. It's been a while since we've done one of these. Pause the video and work the following. Find sine, cosine of tangent of 15 degrees. I'll give you a hint. You'll need a subtraction problem. All right, if you haven't paused the video yet, spoiler alert, here comes the solution. Solution in 3, 2, and 1. Now, I should mention that there's two subtraction problems you could have used. 45 degrees minus 30 degrees or 60 degrees minus 45 degrees. Both give 15 degrees. So regardless of which one you choose, you should get that sine of 15 degrees is square root of 6 minus square root of 2 over 4. Cosine of 15 degrees is square root of 2 plus square root of 6 over 4. And tangent of 15 degrees is 2 minus the square root of 3. Now you might be thinking these look very similar to the answers we got before. For 75 degrees, here's the one for sine of 75 degrees, which matches cosine of 15 degrees. Now, why would that happen? Why was these destined to be equal? Because 15 and 75 are complements. And when you do the cofunction of a complement, it's the same as the original function of the original angle. As far as 2 minus the square root of 3, the tangent of 15 degrees compared to the tangent of 75 degrees, dirty little trick I did. I'll be honest, when I came up with these answers, I didn't actually use the sum and difference formulas. I knew that this was equal to cotangent of 15 degrees because of a cofunction identity. And then I knew that cotangent and tangent were reciprocals. So to get this, I didn't actually use the tangent subtraction formula. I used the fact that I took the reciprocal of cotangent, rationalized the denominator. And believe it or not, when you multiply these conjugates, you get just one. And it ends up being that. So the more tricks you know, the more paths you have from the beginning to the end.